This video is about how to convert alternating current to direct current. Let's start by understanding the differences between AC and DC. Direct current and alternating current are two types of electricity with currents and voltages that differ in magnitude and direction of flow. Direct current is a type in which current and voltage flow in one direction and with a constant magnitude. Current and voltage do not vary in magnitude in DC. Whereas alternating current is a type in which voltage and current change in magnitude and direction of flow. In converting AC to DC, we are altering the voltage and current that change in magnitude and direction of flow to a steady and unidirectional voltage and current. On an AC circuit shown here, the light bulb is flickering due to varying in magnitude of voltage and current. While we can't see this in real life to our naked eyes, because AC is made to vary in magnitude so fast, but this is what happens in AC. Most electrical devices like cell phones, radios and TVs require a steady voltage and current supply. However, electricity is mostly generated and transmitted as AC because AC is more effective in transmission and generation than DC. In order to charge our cell phones, we need first to convert AC to DC. Our cell phone chargers, laptop chargers, and TV power supply units, commonly found at the back of the TVs, convert AC to DC. When converting AC to DC, there are four stages that are voltage step down, rectification, filtering, and finally regulation. On the first stage of stepping down the voltage, we are reducing the voltage to a value that we need to power our load. Here we are reducing 220 volts to 12 volts. The second stage is rectification. At rectification, we are changing alternating voltage to DC power setting voltage. Alternating voltage is voltage that crosses the zero axis, or voltage varying in magnitude and changing direction. Power setting voltage is voltage that varies in magnitude but flowing in the same direction. The third stage is filtering. At filtering, we are reducing the fluctuations in the rectified voltage and producing a relatively smooth DC voltage. The last stage is voltage regulation. At voltage regulation, we are producing a steady or a smooth voltage which then powers the load. In order to understand this conversion, we are going to use conventional current, which flows from positive to negative. For more on current, check out our video titled What is Current? Let's start by stepping down 220 volts to 12 volts using a step-down transformer. When stepping down the voltage, we are increasing the current. This increased current is the maximum current that can be produced by the secondary side of the transformer. However, the load resistance will then determine the current through it with respect to the applied voltage. A transformer has two windings, the primary winding and the secondary winding. When stepping down the voltage, the secondary winding is made to have fewer turns than the primary winding, depending on the level of stepping down the voltage. After stepping down the voltage, we then convert alternating voltage to DC power setting voltage using a rectifier. There are several rectifiers used, including half-wave, full-wave, bridge, and silicon-controlled rectifiers. A bridge rectifier has four diodes that are connected in a way that when AC flows in the first direction, two diodes are forward biased, and when AC changes direction, the other two diodes are forward biased. When diodes are forward biased, they allow current through them and the load. This process of rectifying eliminates the change in direction to DC power setting voltage. A half-wave rectifier is one diode that is connected in series with the load. In a half-wave rectifier, when AC flows in the first direction, the diode is forward biased and current flows through the load. When AC changes direction, the diode is reverse biased and current is blocked. In a half-wave rectifier, the other AC half cycle is wasted. This type of rectifier has an efficiency of 4.6%. A full-wave center-tap rectifier is a rectifier that uses two diodes connected to the secondary side of a center-tapped transformer. In a full-wave rectifier, when AC flows in the first direction, one diode is forward biased and current flows through the load. When AC changes direction, the other diode is forward biased and current flows through the load. After rectifying the voltage, we then filter it. At filtering, we are eliminating the fluctuations in the DC rectified voltage to a nearly smooth voltage. Capacitors and inductors are used for filtering. There are several filters used, such as capacitor filters, series inductor filters, choke input filters, and capacitor input filters. When using a capacitor filter, we connect a capacitor in parallel with the load. In every half cycle of AC during an increase in current, the capacitor charges, and when voltage starts to decrease, the capacitor discharges through the load, eliminating the fluctuations in voltage to a relatively smooth voltage. When using a series inductor filter, we connect an inductor in series with the load. An inductor resists changes in current flowing through it. When current flows through it, it charges and at the same time opposing an increase in current through it. When the current starts to decrease, the inductor releases voltage trying to keep current the same. This helps eliminate fluctuations in rectified voltage. After filtering the voltage, the last stage is regulation. At voltage regulation, we are maintaining a constant or smooth voltage across the load from a nearly smooth filtered voltage. Zener diodes and transistors are used for voltage regulation. In this video, we are going to use a zener diode in our voltage regulation. For a zener diode to regulate voltage across the load, we connect it in reverse to the DC input voltage and in parallel with the load. Zener diodes are mainly designed to work in reverse, although they can work in forward just like a rectifier diode. One important characteristic of a zener diode and also other diodes, unlike other electronic components like resistors, is that when a diode starts to conduct, the voltage drop across its terminals does not continue to increase as the supply voltage and current are increased. The voltage we want to be constant across the load must be equal to the zener voltage. Zener voltage is the reverse voltage at which a zener diode starts to conduct when connected in reverse. For example, let's say the voltage needed across this light bulb is 9 volts. The zener voltage of this zener diode must also be 9 volts. Any voltage increase above the zener voltage, which is 9 volts on this zener diode, causes the zener diode to start working as a short circuit to that voltage, which then stops further increase in current and voltage through the load when the supply voltage increases above 9 volts. The resistor connected in series with the two components, the load and the zener diode, prevents an increase in current through the zener diode path to values such that damage occurs to the zener diode. What happens when we have a shorted path in an electrical circuit? All the circuit currents and voltages use that path because of its zero resistance. This is what happens in a zener regulation circuit. Any voltage above the zener voltage uses the zener diode path instead of the load path because the zener diode path will have a zero resistance to that voltage, thus maintaining a constant voltage across the load. Okay guys, that is it for this video. I hope you find it helpful. Catch you in the next videos.